So what is a limit? What does that notation mean off to the left? How do you even say it? Well, if we had this graph of f of x, we could say that the limit of f of x as x approaches a equals L. And we can do that if we can show that the values of f of x become arbitrarily close to L. Now, arbitrarily close means as close as we want to get to that height of L. And how do we do that? By taking x to be sufficiently close to a. Now, sufficiently close is not the same as arbitrarily close. There's a slight difference. Sufficiently close means as close enough to a as we want to be. Notice I said close to a. I did not actually say it had to equal a, which means not only is this graph a representation of the limit of f of x as x approaching a equaling L, but so is this graph, even if f of a doesn't even exist, if there's a hollow point in the graph at that particular height. Or, let's take it a step further, there is a hollow point at that height, and yet f of a is defined yet somewhere else completely. We're only interested as it approaches a, not actually what occurs at a. Another way we can show the limit of f of x as x approaches a equals L is if we can show that the absolute value quantity of f of x minus L, which is the distance the limit is from f of x, becomes arbitrarily small. Now we're going to stop our definition briefly here, modify the first two graphs by extending out the height of limit L. Then we're going to take a value of x in the first graph, put it in a position where f of x, the height, is going to be lower than the limit L, so that when we find the height's difference, we would actually find it to be a negative value when we go f of x minus L. The second graph, we're going to find a value of x that puts f of x above the limit. So when we go f of x minus L here, we're going to get a positive value. Now those differences between those heights is the distance that I'm talking about. But see, distance is supposed to be expressed as a non-negative value. So if we use those absolute values, now I can guarantee that those difference in heights will always be greater than or equal to 0. And our goal is to get this to be arbitrarily small, essentially as small as we want, by taking x to be sufficiently close, again, close enough to a. But again, let's not worry about it equaling a itself. This definition is much closer to the formal definition of a limit. To help us better understand limits, let's take a look at a limit that will exist. And for that, we'll use the function f of x equals the fraction x minus 1 all over x squared minus 1, and we'll find the limit of f of x as x approaches 1. You may think we should actually start at 1. And so if we go ahead and plug 1 into f and substitute our x's with 1's, you'd find our numerator would equal to 0 and our denominator would equal 0. Now this is going to be known as an indeterminate form of 0 over 0, or simply indeterminate at x equals 1. Now we will get into indeterminate forms in a future video, but for now we're not worried about that so much. We're more interested in the fact that we divide it by 0, which means we have f of 1 being undefined, which is why we have a hole in the graph. Now this might be an issue in other cases, but we're finding limits, and limits do not worry what happens at 1. Limits worry about when x's are close to 1. So undefined or not, we're going to keep going. And we're going to start taking values on both sides. We're going to look at what happens when x is getting closer from the left side, and we'll say start at 0. And we're going to look at what happens as x gets closer from 1 from the right side. We'll start at 2. And so you'll notice that f of 0 works out to be 1, f of 2 works out to be 1/3. Yeah, that's nice. I don't, however, feel I'm close enough, sufficiently close enough to 1 so that I can warrant what my limit is. Let's get closer. Let's go 0.5 and 1.5. Well, now I'm at the fractions 2/3 and 2/5 respectively. I have a better idea what my limit might be, but again, I don't feel I'm close enough to 1 to determine my limit. All right, so we'll get closer still. Let's go 0.9 and 1.1. Well, as you can see by the fractions, and also with the graph, I am kind of homing in onto a specific height. But I feel I need to get closer still. So let's go 0.99 and 1.01. Okay, now I'm between 0.50251 and 0.49751. In fact, those points I can barely see on the graph because they're so close to 1 that, that hollow dot's kind of, covering them up. but I still don't feel I'm sufficiently close. Let's go closer. You know what? Let's go closer still. Now with these values, I feel I am sufficiently close enough to say that the height is 0.5. I feel I'm arbitrarily close enough to say it's 0.5. And that's what I'm going to do. And that's the limit for f of x as x approaches 1. The height is 0.5. Let's do another example in which the limit will exist. And for that, we'll set the function g of x to equal sine of x all over x. And then we'll find the limit of g of x as x approaches 0. Like the last problem, maybe we'll start at 0 and we'll plug it into g. And again, we'll have a numerator and a denominator that are both equal to 0. And we have an indeterminate form. But more importantly, we are dividing by 0, which means g of 0 is undefined. And we'll have a hollow dot at x equals 0. Now, in this case, we do have the graph of g of x here, and I see it as symmetric with respect to the y-axis. Therefore, it's an even function, which means the positive and their corresponding negative x values are going to share the same height. So in this case, negative pi over 2 and positive pi over 2 both have the same g value of 0.63662. Now, just because they're both the same does not mean I've necessarily found my limit. I don't feel I've been sufficiently close to 0 to establish that. So let's go negative pi over 4 and positive pi over 4. It's a good thing I did because I have values of 0.90032 for both of them. Let's get closer still. Let's go negative and positive pi over 6. Okay, I see I'm getting closer and closer to 1. Let's see if that continues. Let's look at both positive and negative pi over 12. Positive or negative pi over 24, and positive or negative pi over 48. Well, by this point, I have 0.99929. Okay, I feel I am sufficiently close enough to say that my limit equals 1, and that's what it is. On this slide, I've decided to tweak my g of x function so that g of 0 would now be defined. In order to do so, I needed a piecewise formula. And my piecewise formula says g of 0 equals negative 0.4. And this allows me now to put a solid dot right on the y-axis at the height of negative 0.4. How does that affect my limit of g of x as x approaches 0? It doesn't. Again, it does not matter what happens as x equals 0. It only matters what happens as x gets closer to 0. And my heights are getting closer to 1. I could have set g of 0 to be any height whatsoever. It's not going to have any impact on the limit. Again, it's all about being close to your value, not necessarily what actually occurs at the value of a, which in this case, a being 0. Let's move on to an example in which the limit will not exist. And for that, I set up h of x to equal the absolute value of x all over x. And we'll find the limit of h of x as x approaches 0. And I'll go through the steps again and show you that if I stick in 0, I'll get 0 divided by 0. And because I'm dividing by 0, it's undefined. Okay, good. I chose this function for a reason, first off, with an absolute value to emphasize that an absolute value in itself is a piecewise function. See, if you take, let's say, the absolute value of negative 4, and you get 4, how does that mathematically work? Well, you have to take the opposite of negative 4. Well, opposite is a negative. So literally you're taking the negative of a negative 4, and that's how you get 4. And that's why the first half of the function, for all values less than 0, you take the opposite value of x. But when it's already positive, or at least 0, you don't have to do any of that. And so all greater numbers greater than or equal to 0, we're just going to leave it as x. So I really can rewrite h of x to equal two parts. The first part, I just replace negative x, and then that gets divided by x for all numbers less than 0. I take the second part and put x in the numerator, divide that by x for all values x greater than 0. Remember, I'm not going to include 0 because we know it's undefined. So if I actually start plugging in values and I look at what happens at negative 2 and 2, well, negative 2 gives me the value of negative 1, 2 gives me the value of 1, and I could actually keep doing this for values closer and closer to 0, and you'll notice that the left side's always going to negative 1, the right side's always going to positive 1. In fact, just think about this. Negative x divided by x simplifies as negative 1 for all values less than 0. And on the right side, it's all x divided by x is always going to equal 1. So that works for all values greater than 0. So my left side and my right side are going to two different values. They're not going together. That's why this one does not exist, or as we abbreviate it, DNE. We'll do one more example in which the limit does not exist. And for that, we will set up a function j of x to equal sine of pi over x, so that we can then take the limit of j of x as x approaches 0. And to be consistent like my prior examples, we will start with the value of a, which in this case is 0, and we will find that j of 0 equals sine of pi over 0, and pi divided by 0, or any number divided by 0, means yes, j of 0 in this case is undefined. All right, we've done what we normally do. So now what we're going to do is take values on the left side of x and the right side of x, and we're going to get them closer and closer to 0. And we'll begin with both positive and negative 1, and when we plug them in, we find out that j of negative 1 and j of 1 are both 0. Okay, let's bring in those x's closer to our value of a, and we'll go plus or minus 0.1. And they both produce results of 0. As well as negative and positive 0.01, as one that's even closer, and closer still. So it seems that all our values on the left side seem to always be equaling 0. All the values on the right side seem to equal 0. Makes sense that we would then assume that the limit as sine of pi over x as x approaches 0 equals 0. But that would be a contradiction to the title of our slide, which says the limit does not exist. And I'm going to do that by using values of negative 2 and 2. Now you might say, wait, the idea of those numbers are needing to get closer and closer to 0. You just went negative 2 and positive 2. I did, because what I wanted to show you is the left side wasn't always equal to 0, and the right side wasn't always equal to 0. In fact, what I'm going to do is now give you some new In fact, what I'm going to give you right now is a brand new table of values. And so you can see I'm including plus or minus 0.3, plus or minus 0.04, and so on. And if we look at the different values of j of x, you will see that not all of them, there are still some that are 0, but not all of them are 0. And if we look at the graph on the left, you'll notice that I have some dots that are at different heights. Some are close to 1 and negative 1. They do kind of look like they're on top of each other. They're not. They're just, those dots are just so close together that, it seems that way. And you might feel that there isn't a pattern, which of course there's got to be, because it's based on a function j of x. So let me help you show you the pattern. This is what the graph actually looks like. And what you see here is that as we get closer and closer to 0, we're not actually getting closer to any kind of number. In fact, let me zoom in between negative 1 and 1, and you can see what happens is the graph actually oscillates between negative 1 and 1. And the closer we get to that 0 value, the more it oscillates faster. And that's why this problem actually is a limit that does not exist, because it is not going to one specific value. How do we know when a limit exists? For that, we have to also know what are one-sided limits. See, the limit of f of x as x approaches a equals L. And let's briefly pause. Remember that the limit equals L, therefore it exists. All right, so let's start again. The limit of f of x as x approaches a equals L. If and only if the left-hand limit of f of x as x approaches a and the right-hand limit of f of x as x approaches a both equal the same limit L. That's how you know a limit exists. But now what I want to do is focus on those one-sided limits. And we'll start with the left-hand limit. Look at the notation. It has x approaching a with a negative symbol. Why is that? Well, wherever you put a on the number line, on the x-axis, negative infinity will always be to the left of that. Therefore, that's the left-hand limit. And if we look at the notation for the right-hand limit, you'll see that x approaches a with a little positive symbol. Well, positive infinity will always be to the right of that value of a, and that's why we'll say that's the right-hand limit. Let's take a look at this graphically. In this case, in the blue curve that goes down, we would say that that's the limit of f of x approaches a from the left. That's another way of saying a left-hand limit. See, what happens is you're on the left side and you're moving towards the right towards a. And in this case, the curve's heights are kind of dipping down to a height of m. On the other hand, we have a limit of f of x approaching a from the right. That's where you're already on the right side and we're moving towards the left, getting closer to a. In this case, the heights are working their way upward to a height of n. Well, the limits m and n do not equal each other. And because they do not equal each other, we cannot actually say that the limit of f of x as x approaches a, no little plus, no little minus, the limit of f of x as x approaches a does not exist. We cannot get those two left-hand and right-hand limits to match up to each other. So, does not exist. On the other hand, with this graph, you will see that our left-hand limit of f of x as x approaches a equals m. Our right-hand limit of f of x as x approaches a equals m. And since both limits, the left hand and the right hand, both equal the same limit of m, we can say that the limit exists, and that's what we do. We say the limit of f of x as x approaches a equals m. Let's return to our 4 prior examples and look at the one-sided limits for each of them, and then determine if those one-sided limits equal each other, and then say if the limit exists or does not exist for each value of a. For instance, f of x equaling the fraction x minus 1 all over x squared minus 1. If we look at the left-hand limit of f of x as x approaches 1, you'll notice that the graph kind of highlights that section in blue. And we start at the left, and we move closer to 1, moving right. You see that it goes to a height of 0.5. The right-hand limit of f of x as x approaches 1, now the graph highlights in green that if we move from the right to left, as we get closer to 1, it also goes to 0.5. And that's why we can say that the limit of f of x as x approaches 1 exists, and more specifically equals 0.5. G of x equals sine of x over x. Let's take a look at the left-hand limit. In this case, the left-hand limit as x approaches 0 goes to a height of 1. Think left to right. The right-hand limit of g of x as x approaches 0 equals 1. Think right to left. Both heights go to 1, therefore the limit of g of x as x approaches 0 exists. It equals 1. H of x equaling the absolute value of x. The left-hand limit of h of x as x approaches 0 equals negative 1. The right-hand limit as x approaches 0 equals positive 1. Those heights do not equal each other. Those limits do not equal each other. Therefore, the limit of h of x as x approaches 0 does not exist. And finally, j of x equals sine of pi over x. The left-hand limit does not exist because it oscillates. Right there, that would be enough for us to say that our limit overall does not exist. But, just to show you that the limit on the right side does not exist either, and again, it doesn't matter which side does not exist. Once one side does not exist, the whole limit x approaching 0 does not exist.